Hello everyone and welcome back to another video. In this video we're moving on to chapter 4, which is all about differential equations, and we're going to briefly explore differential equations. And differential equations are super powerful and super popular in mathematics, especially applied mathematics, because many real-world phenomena can be modeled mathematically using differential equations. For example, population growth, radioactive decay, predator-prey models, and even my research that I did for my master's thesis on the stratospheric polar vortex. The model that I was studying was actually a system of 3 ordinary differential equations. And so differential equations, right, you can either have ordinary differential equations, which means that it depends on one variable, and partial differential equations, which involve derivatives with respect to more than one variable. So the reason why, right, so section 4.1 is going to be all about the basics of differential equations, and a short phrase that's used for differential equations is diffie-qs. So the reason why diffie-qs are so useful is because, right, let's define them. A differential equation, right, or diffie-q is an equation involving not only a function y, which when you're talking about a differential equation, the function y is what we solve for. So that's why we call it an unknown function y equals f of x. But it involves, so a differential equation is an equation involving an unknown function y and one or more of its derivatives. And that's where differential equations get their names, right? Because remember that differentiation was the process of finding the derivative. And so that's why they're called differential equations, because they use derivatives. And remember that a derivative, right, that's pretty much synonymous to a rate of change. That is what a derivative describes, right? Remember, the derivative is the slope at a specific point. So this was the definition for a differential equation. And so this change, that is all that we've been studying in calculus. And why we even study calculus is because calculus is the mathematics of change. And how do we study how things change over time? That's where derivatives come to play, right? So rates of change, as I just wrote right here, are expressed by derivatives. And so since differential equations use derivatives on top of just using the function itself, right, differential equations are able to incorporate how things change. So since diff EQs involve derivatives, right, they're able to capture how things change over time, right? And the thing is going to depend on what the function is even representing. Okay. And so, like I mentioned earlier, right, the reason why we call this an unknown function, right now we're going to define the solution to a differential equation, and it's actually going to be that function y that satisfies the differential equation. So a solution to a differential equation is a function y equals f of x that satisfies the differential equation when you plug that function f and its derivatives into the differential equation. So basically, right, when you plug in a function y and any of the derivatives that are in the differential equation, you should get a true statement. And one thing that's important to note before we do an example is that solutions to differential equations are not unique. Solution to a differential equation is not unique. Why? Well, remember the derivative of a constant is 0. Okay, so let's do an example where we show that something is a solution to a differential equation. Okay. Oops. Okay. So we're going to verify that the function y equals e to the negative 3x plus 2x plus 3 is a solution to the differential equation y prime plus 3y equals 6x plus 11. So remember, when we talked about the solution, right, that's a function y equals f of x. So they're giving us the function here that satisfies the differential equation when f and its derivatives are plugged into the differential equation. So basically what we have to do is plug in our f and its derivatives into our differential equation, and if it gives us a true statement, then we know that it is indeed a solution, right? So we know that in this function we see y, which we know y is e to the negative 3x plus 2x plus 3, so that's what we would plug in there. But here, right, we have to find y prime. So y prime, remember, is the derivative of y. So we have to find the derivative of e to the negative 3x plus 2x plus 3. Right, so remember that we can use here the chain rule technically, so the derivative of the inside is negative 3, and then the derivative of the outside is just e to the x, with the inside plugged back in is just e to the negative 3x again, and then the derivative of 2x is just 2. So now we have our y and our y prime to plug into the differential equation. So plug y and y prime into the differential equation. Right, so this is our differential equation here that they gave us. So y prime is negative 3e negative 3x plus 2, and then we have 3 times y, which was e to the negative 3x plus 2x plus 3, and that's all equals to 6x plus 11. Right, so the first thing we're going to have to do using PEMDAS is distribute this 3 to all of those terms. So we have negative 3e to the negative 3x plus 2 plus 3e to the negative 3x plus 6x plus 9. Okay, so then when we see that, we have a negative 3e, negative 3x, and we have a positive 1, so those cancel. And then we can add the like terms, 2 plus 9. And so that's going to give us 6x plus 11 is equal to 6x plus 11, which is true. Right, so since this is a true statement, right, so that is the left-hand side equals the right-hand side, we know that y equals e to the negative 3x plus 2x plus 3 is a solution to the differential equation y prime plus 3y equals 6x plus 11. Okay, so that's that. So basically, if you're given the solution, you need to find any derivatives that are present in your differential equation and plug those into the differential equation, the y and the y prime. And remember, that's what the solution to a differential equation is. It's a function that satisfies a differential equation when f and its derivatives are plugged into the differential equation. So something else that's important to talk about when we're talking about differential equations is the order of a differential equation. And this is pretty straightforward because the order of a differential equation is the highest order derivative that appears in the differential equation. So we're talking about order of differential equations, and we'll see this is important later on. But right, when we're talking about this differential equation here, this differential equation, the highest derivative is the first derivative, right? We don't see second derivative, third derivative, fourth derivative, none of that. So the order is 1. Okay, so let's do a couple more examples. Right, what is the order of each of the following differential equations? Right, so A is x squared y triple prime plus 3x4 plus xy prime minus 3y is sine x. And then we'll do B, which is 4 over x y to the 4 minus 6 over x squared y double prime plus 12 over x4 y is x cubed minus 3x squared plus 4x minus 2. So it's important when you're doing these to not confuse exponents with derivatives, right? So we're not looking at exponents of x, we're looking at derivatives of y, right? So this is the third derivative, right, when we see y with 3 apostrophes, and this is the first derivative, and those are the only derivatives present. So the highest one is the third derivative, so the order of this differential equation is 3, right? And when we move on to the second one, right, for the second one, we have this fourth derivative, second derivative, and right, there's an imaginary zeroth derivative for the function itself. So here, the fourth derivative is the highest, and so this has order equal to 4. Okay. So I think I want to stop there for this video, and we'll finish off the section excuse me, in the next one.